All right, so today we're looking at rotational inertia. I think what you'll see once we get through most of this is there's a lot of similarities to regular inertia that we talked about back in chapter 4. And remember, inertia was based on the mass of an object. Inertia is the tendency of an object to resist acceleration. And so if an object has more mass, then it resists acceleration more. You'll see some of the same similarities here, but now since we're talking rotational dynamics, things change up just a little bit. But let's kind of define these first, and then we'll get to more of the technical stuff. If something has high rotational inertia, what that means is it's going to be slow to start up, and then likewise, when you go to stop it, it's going to be slow to stop as well. And again, that's just like regular inertia, resisting acceleration. So I'm going to write that in here. High rotational inertia means slow to start and also slow to stop. So most of the stuff in this chapter, we're talking about something spinning. A lot of these things will be something rolling, like down an incline or rolling across the surface. And in this case, those would be really slow to start rolling. And then once it does get going, it's going to have the tendency to keep going, and it's going to be slow to stop. The opposite of that, obviously, here is going to be low rotational inertia, which means it's going to start spinning or rolling really fast. So fast to start. And then also, it's going to be fast to stop as well. So if it's coming to a stop or you're applying some kind of a torque to it, it's going to slow down pretty quickly because of this low rotational inertia. All right, so that's kind of the run through in terms of what this stuff is. In order to determine the rotational inertia of an object, so we'll get a little technical now, there's some things that we have to know. So something called center of mass plays a role. So I'm going to write that out, center of mass. We have kind of ignored that topic so far. A little bit in free body diagrams, if you remember, we would draw a box to be our object, and in the middle of that box we would put a dot. That dot always symbolized the center of mass of that object. We didn't go into a whole lot of detail about that at the time because we saved that until now to talk about, but that's what that meant, so we have seen it a little bit. But when we're talking about center of mass, we're talking about the point at which things rotate around when we're talking about rotational dynamics. And so basically it means kind of the center of the object. It's kind of the balancing point of the object. Just trying to think of different ways to describe center of mass. And depending on where the center of mass is for the object, it's going to influence its rotational inertia. And so there are certain objects that will have high rotational inertia and some that will have low. And we're going to look at three specific types of examples, three specific objects that will deal with center of mass. We'll also in class go through a bunch of kind of little mini labs and things to get the idea for center of mass. One type of object that we're going to look at is a hoop, or something like a mass on a string that's being like kind of rotated around the top of your head. So mass on string, let's put that on here as well. And so just to give you a quick view of what this would be, what a hoop is. A hoop, if you think about it, we're going to try to do a decent drawing here. Here's kind of the outer edge. The center of mass of the hoop is going to be right in the middle of it. But also, if you kind of look, so this is kind of almost like a bicycle wheel or that sort of thing. All of the mass is located out here along this outer edge. That's what makes it a hoop. The center point's right in the middle. That's the point at which everything will spin around, so that's its center of mass. You could also have, this drawing may not be as good, you could have a mass on a string, so if that's kind of a little holder, and then you got this string with a mass out here on the end, and you were to spin this thing around like this, those situations would be identical in terms of the rotational inertia. Because the mass is far away from the axis of rotation, if you notice it's all on the outside here, and then up here also it's all on this outside. Because of that, the rotational inertia here is going to be high. And so in other words, these are going to be very slow to start and then very slow to stop as well. The equation that's going to describe that is rotational inertia is abbreviated with a capital I, which is kind of nice, that makes sense. And then we have to think about what's going to influence this rotational inertia. If it were just a regular object and things weren't spinning or rolling, then all we would say is inertia is mass. But now we're concerned with not just mass, although that does play a role, but we're also worried about or concerned about where it's located. And so in this case, the mass is located kind of far away from this radius. And so that's going to play a role, like where is that mass at? And so this is the equation. So rotational inertia is mass times radius squared. A lot of times I think people, just for fun, end up saying Mr. Squared here, just as a way to identify this particular setup for this hoop or mass on a string. So this rotational inertia is Mr. Squared. We're going to compare this to other objects, what other objects are going to look like, and we're going to end up with, I think, some different numbers here. So draw a little line here, and let's say, well, what if we don't have a hoop? What if instead of a hoop here, what if all this area were filled in and we had a disk? So this is going to work for disc-shaped objects that have kind of a solid area through here instead of a hollow area. And so now we're looking at still round object capable of spinning or capable of rolling. Axis of rotation and center of mass still right there in the center point. But now this is all going to be filled in. I'll try to do that with a different color. We'll see how that shows up. So that all of this is now solid. We got a solid disk. I think that's probably good enough. You get the idea. So now that we have the solid disk, look at where the mass is located in comparison to that center axis of rotation. Right here, you have mass that's now closer to it. The closer you get mass to that axis of rotation, the lower the rotational inertia is. So in this case, because this is a solid disk, the rotational inertia is going to be less than a hoop. And in fact, the equation, which sets up very similar, but it now has a 1/2 in it. So now you can see clearly with that 1/2 that the rotational inertia of a disk is less than that of a hoop. And that's based on its mass, a lot of its mass being located more centrally close to that axis of rotation there. So that's a disk. Anything that would be solid would follow those principles. Just to give you, I guess, a view of something, like this is a hoop. This is the metal ring. This would have a high rotational inertia. In other words, it would be very slow to start. You sit this down on an incline and you start to roll it, it'll start rolling, but it's going to start very slowly. Compared to the disc, looks something like this. You can see it's solid. It's got more of that mass located towards the center, which lowers its rotational inertia. So this guy's going to speed up a lot faster on an incline if this were rolling down an incline. So just to give you a couple visuals there. That's the disk. The final object that we're going to look at, let me draw a line here, is going to have even a lower rotational inertia. And here we're going to be talking about spheres. I've got no hope of drawing a good sphere, but I'll go ahead and draw one anyway. I'll try to do that fancy shading that I see them do with spheres sometimes, with the light source and all of that. I'm sure it won't turn out, but there it is. There's the sphere. If you think about the sphere and apply the same stuff that we've talked about up here, think about the mass of a sphere and where it's located at. The axis of rotation is still, because this is a geometrically perfect shape, it's still right in the center. So the center of mass is right there. It's all going to rotate around that center point. But now think about the mass. And not only is it close to the center like it is in a disk, but now it's around that center point in a three-dimensional shape. So it's like packed in not only on left and the right and up and the top, but in front of it and behind it and all that stuff. So because that mass is now even more centrally located, that's going to mean we get one of the lowest rotational inertias of all, which is going to lead to an equation that looks like this. We're going to have 2/5 Mr. Squared on this guy. And so you can see from the fractions, this rotational inertia will be smaller than a disk, and that will be smaller than a hoop. So you can kind of see the order. These equations are not on the AP equation sheet, so be careful with that. You'll have to memorize them, but after you use these a few times, it's pretty easy, I think. You just have to kind of remember hoop versus disk versus spheres. We can use any of these equations to get our units for rotational inertia. We'll just use this starter one up here, and it's just as easy as filling in our units here, which we have write it over here just so it looks a little more together. So we've got mass measured in kilograms, and then we've got R, which is our radius, times meters, and that gets squared. So just using the equation to help. Those are the units for rotational inertia. It doesn't matter which of these scenarios. A lot of times this is kind of the starting point to some of the more complicated problems that we'll get to. So sometimes we're solving things that are involving rotational energies or rotational angular momentums, things like that. And a lot of times you have to know the I value before we can do any of that. So these will be pretty important as we move forward. So hopefully that makes some sense. The last thing to look at, so that's rotational inertia. The last thing we're going to look at today is applying Newton's second law, which by now hopefully you can recite as F equals ma, one of the more important equations that we work on. And we're going to adapt this to angular and rotational quantities. So just like we've been doing with some of the other equations that we fit in this chapter, we're going to do the same thing here. And we're going to use this as our starting point. When we've dealt with things that are rotating, not only do we deal with the amount of force that gets applied to them, but we also deal with where that force is located. And if you remember, that's basically the description for torque. So rotating objects, and that's the Greek letter tau, if you remember it, torque is a force that's located some distance from an axis of rotation. So it's not just force, it's where it's located, that's torque. Now, since things are spinning and rolling, it's also the same. It's not just mass, but it's where the mass of the object is located at, which we just did a decent job, hopefully, of defining as rotational inertia. That's capital I. So you see the mass get replaced with rotational inertia here. And then finally, because things are spinning or because things are rotating or rolling or whatever they're doing, it's not a linear acceleration, it's now an angular acceleration, and so we have alpha there as well. So we've just taken Newton's second law and adapted that with our new quantities that are similar but a little bit different because of our concentration of looking at where mass is located to get our new equation for torque.